acephysics.org. Math and Physics Tutoring with Dr. Hudis. I'm going to be solving some problems involving capacitors in series and capacitors in parallel. In this schematic diagram here are three capacitors in series. There's a battery and three capacitors in series. Capacitors in series have the same charge. In order to solve for equivalent capacitance for capacitors in series, 1 over CEQ, that's the equivalent capacitance, is equal to 1 over C1 plus 1 over C2 plus ... In this case, ... is 1 over C3. If you had 4 capacitors, it would be plus 1 over C4 and so on. Now, the reason that capacitors have the same charge when they're in series, imagine that a positive charge leaves the battery and it moves up here and it hits the capacitor and it gets stuck to the capacitor. That's this positive charge plus Q. That positive charge is going to put an electric field and cause a positive charge to move from the bottom plate. And then that positive charge is going to go to the top plate of this capacitor, which is going to push a positive charge off of here, leaving the bottom plate negative, and then the positive charge will go here, and the negative charge will move here until the voltage is equal to the voltage of the battery. And so all of these charges, this plus Q, and this plus Q, they're equal. And this negative Q and this negative Q and this negative Q is equal, and the magnitude of plus Q is equal to the magnitude of negative Q. So capacitors in series have the same charge. Here's a battery and two capacitors in parallel. By the way, I should say, when you have two lines and one is longer than the other, that's a battery. When you have two lines that are the same length, that's a capacitor. Capacitors in parallel have the same voltage, just like resistors in parallel have the same voltage, and the equivalent capacitance for capacitors in parallel is C1 plus C2 plus ... This is the first of three problems I'm going to do in this presentation. In the below figure, 220 volts is applied between points X and Y. This is point X, this is point Y. There's no battery here. We're going to assume that you connect this up to a 220 volt battery. What is the equivalent capacitance of the circuit? Calculate the charge and potential difference across each capacitor. The first thing we do is we want to find the equivalent capacitance. So to find the equivalent capacitance, you start out with your initial schematic and you take two capacitors and then you add up all the capacitors until you're left with only one capacitor. I notice that this capacitor and this capacitor, these two 4.2 microfarad capacitors, are in series. So 1 over CEQ equals 1 over 4.2 microfarads plus 1 over 4.2 microfarads. That's 2 over 4.2 microfarads. Therefore, the equivalent capacitance is 2.1 microfarads. I can replace these two capacitors that I circled in red with one capacitor of 2.1 microfarads. And now this circuit is equivalent to the circuit above it. This schematic is equivalent to the one above it, which is to say any voltage source that I put on this circuit would have the same exact response to what I put on this circuit. Now I notice that these two capacitors are in parallel. So I can just add these two up in parallel. 2.1 plus 4.2 is equal to 6.3. And then I can replace these two capacitors with one single capacitor of 6.3 microfarads. Now I have three capacitors in series. And so I can add these three capacitors up to get an equivalent capacitance. 1 over the equivalent resistance is 1 over 8.4 plus 1 over 8.4 plus 1 over 6.3 microfarads. And this tells me that the equivalent capacitance is 2.52 microfarads. This one capacitor is equivalent to this circuit right here. Okay, so that's the equivalent capacitance. What is the equivalent capacitance of the circuit? That's it. Calculate the charge and potential difference across each capacitor. So now what you do is you start at the bottom and then you work your way back up. I have to say it's pretty tedious. It's awful. These problems are not exactly fun, but they're important. This will help you become a better physicist, a better person, and it will, just make your life a living hell. Okay, so here's a 220 volt source, and this is attached to the capacitor of 2.52 microfarads. We want to find the current and the voltage across this. The charge and the voltage across everything. Q is equal to CV. That's the fundamental formula for capacitors. C is given. It's we just calculated it, 2.52 microfarads, and we're talking about a 220 volt battery. Therefore, you have 5.54 times 10 to the negative coulombs of charge on this capacitor. Now, this capacitor decomposes into these three capacitors, and we just did this. So we're just working our way backwards. I just take the pictures that we had before, and I'm working my way backwards. Now I know that capacitors in series have all the same charges, which means all of these capacitors have a charge of 5.54 times 10 to the negative 4 coulombs. That's the charge on all these. And then I can find the voltage across the capacitors by saying V equals Q over C. So the voltage across this capacitor is Q, 5.54 times 10 to the negative 4, divided by 8.4 microfarads. That's 65.9 volts here and here, because these are the same capacitor values. And then this capacitor is a different capacitance value. V is equal to Q over C. The Q is 5.54 times 10 to the negative 4. Here, the C is 6.3 microfarads, and that's 87.9 volts across this. Now, this capacitor decomposes into two parallel capacitors. And I know parallel capacitors have the same voltage, so both of these two capacitors have 87.9 volts across them. How do I get the Q? Q is equal to CV. I know the C's, and so 2.1 microfarads times the voltage, 4.2 microfarads times the voltage. That gives me 1.8 times 10 to the negative 4 coulombs here, and 3.7 times 10 to the negative 4 coulombs here, and they both have 87.9 volts. Then I work my way backwards once again, and I notice that this one capacitor decomposes into two series capacitors. Both series capacitors have the same charge. That's the charge of 1.8 times 10 to the negative 4 coulombs. And so both of these capacitors have the same charge, which is 1.8 times 10 to the negative 4 coulombs. V equals Q over C. I know Q. They both have the same capacitance value, 4.2 microfarads. And we have solved the problem. So this is the final answer. The final answer is this was the circuit that was given to us. This 8.4 microfarad capacitor has 65.9 volts across it and 5.54 times 10 to the negative 4 coulombs. And these are all, you can see all the other numbers. This capacitor in the center, it's a 4.2 microfarad capacitor. It has 87.9 volts across it and 3.7 times 10 to the negative 4 coulombs of charge on each one of the plates. All right, let's try problem number 2. Problem number 2 says, in the below figure, compute the equivalent capacitance, compute the charge in each capacitor if the voltage across point X and Y is 840 volts. I didn't label the X and Y here, but we have to assume there's a battery, an 840 volt battery, which is connected between these 2 points. This can be X and this can be Y. All of these capacitors on the top and bottom are 13.8 microfarads, and the capacitors in the center are 9.2 microfarads. You may want to pause the video and see if you can do this on your own. In order to get the equivalent capacitance, I need to redraw the picture many times until I'm left with just one capacitor. So this was the initial diagram. This is the initial picture, and we want to find the equivalent capacitance. I notice that these 3 capacitors are in series, so I can replace these 3 with an equivalent capacitor. 1 over CEQ equals 1 over 13.8 plus 1 over 13.8 plus 1 over 9.2, and that tells me that the equivalent capacitance is 3.94 times 10 to the 6th farads. That should be negative 6 times 10 to the negative 6 farads. And this one capacitor is equivalent to these 3 series capacitors. Now I notice that these 2 capacitors are in parallel. So I can add these 2 capacitors up in parallel. 9.2 plus 3.94 is 13.14. So this capacitor of 13.14 microfarads replaces these 2 capacitors in parallel. Now I see that there's 3 capacitors in series. 1 over CQ equals 1 over 13.8 plus 1 over 13.8 plus 1 over 13.14. The equivalent capacitance is 4.55 microfarads. And now I see that this capacitor and this capacitor are in parallel. So I just add those 2 up. 4.55 plus 9.2 is approximately 13.8 microfarads. So I'll put that right there. And now we have 3 capacitors in series, which are all the same value. 1 over CQ equals 1 over 13.8 microfarads plus 1 over 13.8 microfarads plus 1 over 13.8 microfarads. And that tells us that the equivalent resistance is 4.6 microfarads. And there's 840 volt battery connected to it because the problem said that. Now the question is to find the charge on each capacitor. And in order to do that, you take the schematic, which is the most reduced. In this case, it just has one capacitor, and in general, that's going to be the case. This is connected to an 840 volt battery, and then we're going to work our way backwards through all the diagrams that we already drew. Q is equal to CV. I know C and I know V is 840 volts. Therefore, there's going to be 3.86 times millicoulombs of charge on this capacitor. This capacitor decomposes into 3 series capacitors, and they all have the same exact charge, 3.86 millicoulombs. The voltage across this capacitor, I'm going to need for the next part of the problem. So the V equals Q over C. I know the Q is this capacitor, and the C value is 13.8 microfarads. Therefore, the voltage across this one capacitor is 278.8 volts. This one capacitor decomposes into a parallel combination of capacitors, and both of these capacitors have 278.8 volts across them because they're in parallel. In order to get the charge on them, Q is equal to CV. Therefore, the charge on this one is 1.3 times 10 to the negative 3 coulombs. We already knew that. And the charge on this one is C times V. The capacitance value is 9.2 microfarads. The voltage is 278.8 volts. And that gives 2.56 millicoulombs of charge on this capacitor. Now, the 4.55 microfarad capacitor decomposes into 3 series capacitors. All of these have the same charge, 1.3 millicoulombs, because the charge in series is the same. V equals Q over C. Therefore, the voltage across the 13.14 microfarad capacitor is 98.9 volts. That capacitor decomposes into 2 parallel capacitors. They have to have the same voltage of 98.9 volts because parallel combination of capacitors always have the same voltage. Therefore, the charge on this capacitor is C times V. I know the C value and I know the V value. The charge is 3.89 times 10 to the negative 4 coulombs. On this capacitor, Q equals CV, and I know the C and the V, and the charge on this is 9.1 millicoulombs. Milli is 10 to the negative 3. And that's the answer to the problem. This is the third problem, and the final problem for this presentation. You are given as many 100 nanofarad capacitors as needed. If you want 10, I'll give you 10. If you want 50, I'll give you 50. I'm going to give you as many as you want. How can you connect several 100 nanofarad capacitors to create an equivalent capacitance or an equivalent capacitor of 50 nanofarads, and then 450 nanofarads, 25 nanofarads, 75 nanofarads? You may want to pause the video and try this on your own. If I have 2 100 nanofarad capacitors in series, the equivalent capacitance is 50 nanofarads. 1 over CEQ equals 1 over 100 nanofarads plus 1 over 100 nanofarads. That's 2 over 100. You invert it, CEQ equals 50 nanofarads. Now, if I want to get a 450 nanofarad capacitor, well, I would want 4 100 capacitors in parallel with a 50 nanofarad capacitor. So this is a 50 nanofarad capacitor, and all of these are 100 nanofarad capacitors. And when they're in parallel, you just add them up. So this plus this plus this plus this plus this is 450 nanofarads, and that's how you do it. What about 25 nanofarads? For 25 nanofarads, C equivalent is 100 nanofarads over N, where N is the number of nanofarads you have in series. If I want to add up several in series, 1 over CEQ equals N over 100 nanofarads, and then you flip it, and CEQ equals 25 nanofarads. That tells you N equals 4. If I add up 4 100 nanofarad capacitors in a row in series, that is equal to 1 25 nanofarad capacitor. And to get a 75 nanofarad capacitor, I can add a 25 nanofarad capacitor plus a 50 nanofarad capacitor in parallel, and I already know how to get a 75 and a 50 because that's something that we just did in this problem.